Okay, so we did 4.1 and 4.2, and then we skipped 4.3 to do 4.4 because it really tied in well with the first two sections. So we're coming back to catch 4.3, and this is where we learned how to graph tangent and cotangent functions. They're a bit different than the other ones. Their period is a bit shorter than the others, and so that's why we kind of leave them for the very end, or at least I do. So I've made my little table or list of all the important information and given you a generic graph for each of these functions. If you look at tangent, tangent follows the domain, the same as, what was it, our secant function, I believe. I don't have my notes on me. Where it's not going to have a value at the pi over 2's. So any multiple of pi over 2, we're going to have an asymptote there that our graph is going to hug, not cross. The range in this case is going to go from negative infinity to positive infinity. If you look at the graph, it shoots up for forever and it goes down for forever. So everything is covered in the tangent and cotangents. Tangent is symmetric to the origin. That means if you take your top right corner and you fold it down, it will cover the bottom left. And if you are symmetric to the origin, that means that you are an odd function. An odd function means that when you put in the negative x's into your tangent, you get negative tangent of x. Like I mentioned, these have a shorter period instead of having a period of 2 pi like all the other trigonometric functions that we've talked about. They have a period of just 1 pi. So if you're asked to graph a tangent or cotangent over 1 period, you're only going to cover pi. If you're asked to do it over 2 periods, then you will cover 2 pi. And either you can go from 0 to 2 pi, or you can go from pi to negative pi, however you would like to do that. Once again, there are no amplitudes for our tangent and cotangent functions, and that's because as you look at the function itself, it extends upward and downward for forever. Thus, there is no amplitude. And a little bit different than 4.4, we do have some x-intercepts, and these happen anywhere that n times pi occurs, where n is an element of the integers. Remember that funky looking z up there stands for the integers. So down here when it says add n over pi, that's where it's going to cross. So if n is 0, then it happens at 0. If n is 1, it happens at pi, 2 pi, 3 pi, so on and so forth. So there are x-intercepts for these. The cotangent is almost exactly the same. It's just it's flipped because it's the inverse. Remember, cotangent is the inverse of tangent. So our domain in this case is not going to include the n times pi. Anywhere that you have a multiple of pi, you're going to have your asymptote. So this is the opposite or the reverse of the tangent above. Your range is still negative infinity to infinity. You're still symmetric to the origin. You still have a period of pi. You still have no amplitudes. And since the domain is excluding those n times pi's, then our x-intercepts obviously can't happen there because that's where the asymptotes happen. So they happen at the pi over 2's. So that's what flips. For tangent, we have our asymptotes at the pi over 2's, and we have our x-intercepts at the pi's. For cotangent, we have our asymptotes at the pi's, and we have our x-intercepts at the pi over 2's. And then as you look at the graph, we start up on our cotangent and go down, whereas on our tangent, we start down and go up. Bless you. Again, they're inverses of each other. And I feel like out of all of the trigonometric functions, the tangent and cotangent graphs are the ones that look most like inverses of each other. All the rest of them take a little bit of seeing just because of how, like sine and cosine, the fact that they're both really wavy, or cosecant and secant, the fact that you're going off of the sine and cosine, it doesn't always stand out as noticeable to me. But these are pretty obvious that if you flip them, you're going to get the opposite ones. Is there any questions on any of the details? Are we okay if I scroll up to where you can't see the tangent stuff? Or at least most of it. Because following all of the information is the how-to part. So how to graph, which this is going to be slightly different, at least different than the cosecant and the secant, because the cosecant and the secant, we had to have our guide graphs, and we don't have to have any of that here for our tangent and our cotangent. So again, I start by giving you the really generic form of the tangent, where you have a tangent bx or a cotangent bx. Again, b has to be a positive. And really, it follows the same steps that we've done pretty much every other section in 4.1 and in 4.2. The one difference is here in the period. When we determine the period, what we're doing is we are determining pi over b. In all of our other functions, we did 2 pi over b. And that was because the period in general for all our other trigonometric functions was 2 pi. But our period here is just 1 pi. And so be careful of that when it comes to actually graphing it, because you've done 3 sections now where it's 2 pi over b, and this is the one section where it will be pi over b. And then they mentioned finding 2 adjacent vertical asymptotes, and they show us that those happen at bx, the positive and the negative of those. We sketch our asymptotes, we divide our interval between the asymptotes into 4 sections, we evaluate the function at those subdivisions, and then we graph using those points. All of that is pretty much the exact same stuff that we've done before. The slight difference is you do want to put those asymptotes in first, because that's kind of your guide. That tells you kind of how big your period is in that one section, and then that's where we do our subdividing. So if we're talking about tangent, our bx is going to equal negative pi over 2 and pi over 2. And then bx for our cotangent is going to be 0 and pi, which we can see that up in our original graphs. While you can't see the asymptote here at 0, you can see the asymptote here at pi. And then we would subdivide between 0 and pi for different units to test so that we know what's going on. If I remember correctly, all of the homework and quizzes for this section, and I think the last section we covered, they were all multiple choice in terms of the graph. You didn't actually have to physically graph any of them on the Pearson site. I could be wrong, but I remember looking through them thinking they were almost all multiple choice. You're ready? If you're not ready, raise your hand. Okay. Then we'll wait. flip over and let's do one. We're going to graph y equals tangent 2x. So even just looking at the general format of this function or of this equation, we should be able to tell kind of what our graph's going to do. Because the same translations occur here with our tangent and cotangent that have occurred for all of our other trigonometric functions and all of the functions that you learned in college algebra. Again, that's 2.5 in college algebra. So what kind of transformation is going on here with that 2x? Yep, it's going to be a horizontal shrink. So remember, if it's inside the function itself, it's always going to be a horizontal something. If it's a number in front of the x, it's a horizontal stretch or shrink. If it's a plus or minus a number after the x, again, inside of your function, then that's a horizontal shift. Anything that's vertical happens outside of your function. If it was a vertical stretch or shrink, it happens at the front. And if it's a vertical shift up or down, again, they usually stick that at the front, but it's still a plus or minus telling you what's going on. But all of those happen outside of the trigonometric functions themselves. If it's inside the trigonometric function, it's going to be horizontal. And so that's just something to note. The first thing you want to do is you want to figure out what your period is. So your period is going to be pi over b. In this case, b is 2. So it shrinks our period from pi to pi over 2. So we're smushing our tangent functions into a smaller space. Step 1 should always be figure out what your period is. And part of that is going to be this new thing where we're figuring out where our asymptotes are. Because once we figure out where our first adjacent asymptotes are, then we are going to be able to determine how to subdivide to figure out our graph. So these asymptotes happen at bx equals negative pi over 2 and bx equals pi over 2. Now, you're like, well, I just wrote that. Yes, you did. Just write that. But what was our b in this case? 2. And so every single time you do this, you're going to have a different b. And so your equation changes slightly. So it's going to be 2x equals negative pi over 2 and 2x equals pi over 2. And you have to solve this equation to figure out where x equals these values so you can figure out where to put your asymptotes. So we're going to stick an asymptote at pi over 4 and at negative pi over 4. And our function then lies between those two asymptotes. Now, in general, if you're doing a matching situation, the information that you have already might be enough for you to go ahead and be able to pick out what graph it's going to be. Because you know that you have an asymptote at negative pi over 4, and you know you have an asymptote at pi over at positive pi over 4. And then you also know that, in general, your trigonometric function looks like this. And so if we have negative pi over 4 and pi over 4, and if you're given a bunch of different graphs, you may be able to go ahead and deduce what's going on just based on that information. So then you would sketch your asymptotes. You would divide the interval from negative pi over 4 to pi over 4 into 4 equal segments. So that gives you the negative pi over 4 at one end. Then you'd have negative pi over 8, 0, positive pi over 8, and positive pi over 4. If you're ever wondering how we're getting those, what we're doing is I take one of my endpoints and I multiply it by the 1/4. Then I multiply it by 2/4, 3/4, and 4/4. Well, not really 4/4 because that gives you 1. But if you take your upper limit and you do that, it will give you all of your little sublimits. And then I did do a table, I think for all of them. Again, you are not required to do a table. They help me to understand what's going on and to figure out where my values are. So those subsections, those dictate what my x's are. Notice I didn't include the negative pi over 4 and the positive pi over 4 in my table. And that's because I'm not actually evaluating my function there because that's where my asymptotes happen. So I'm only actually evaluating my function at the 3 subdivisions in between, that negative pi over 8, the 0, and the pi over 8. So then I take 2 times that, which gives me the negative pi over 4, the 0, the pi over 4, and then I find what the tangent at those various locations is. Because that's going to tell me my ordered pair then to graph on my graph. And my pretty general picture here looks a whole heck of a lot like my more detailed picture up here. I just happen to have a little bit more to show. So tangents will rise as you move from left to right. Cotangents, because of the inverse, will fall as you move from left to right. So what makes this one different than like our secant and cosecant from 4.4 is that we actually do have to computationally compute where these asymptotes are to start with. In secant and cosecant, we didn't do that. What we did is we graphed a guide function of either sine or cosine, and then we found our asymptotes based on those x-intercepts from those guide functions. Do we have any questions on how I graphed this tangent? On how I found where my asymptotes were, or my subdivisions, or anything like that? Okay. Then let's try a cotangent one. I'll try to leave some of the tangent stuff up there too. So we're going to graph y equals 1/2 cotangent 2x. So again, this one's going to have a horizontal shrink or smush by a power of 2 because of that 2 inside the cotangent. But then that 1/2 on the outside is telling me that I'm actually going to shrink vertically down as well. And I will say this, when it comes to shrinking down vertically, our cotangent and our tangent, especially on the graph paper that I'm using, you're not going to see it as much. Because if you notice, our graph extends upward and downward towards infinity. So really all that's happening is it's just not growing quite as quick. And that's kind of hard to note when we get to graphing it on general paper here. So again, we find our period. Since period deals with b and our b is 2, our period once again is pi over 2. Which means that when we go to solve our bx, we're going to put in a 2 for the b. But remember, when we talk about cotangent, bx equals 0, not negative pi over 2 and pi over 2. It's going to equal 0 and pi. So those are 2 things to keep straight. Cotangent goes with 0 and pi. Tangent goes with the plus or minus pi's over 2. But we solve to find our asymptotes the same way. We plug in 2 for our x, and we solve for our asymptotes, finding that we're going to have an asymptote at x equals 0 and at x equals pi over 2. If there isn't any type of horizontal shifting that's happening, you will always end up having an asymptote at 0. Horizontal shifts are the only way your asymptote's ever going to get off of 0 when we talk about your cotangents. And I do one of those. I do one of the big daddy problems here next. So asymptote at 0 and pi over 2. So next we would sketch a graph of those. And we would need to divide our interval from 0 to pi over 2 into 4 equal segments. So we're going to have 0, pi over 8, pi over 4, 3 pi's over 8, and pi over 2. Again, what I did is I took pi over 2 times 1/4, pi over 2 times 2/4, pi over 2 times 3/4. And that gives me my subdivisions. Then we evaluate. I like the table. You could just plug in those values into the original equation and compute out the answer at the bottom row here. That would also work. It saves you having to go step by step. The one reason why I really like the table, though, is because it makes you not rely on the calculator as much. All it takes is one missed negative or one missed set of parentheses, and your calculator is going to compute something completely different. And so with the table, what it does is it allows us to have more information spread out to where whenever I'm going into it, I'm just taking 1/2 times 1. I can do that in my head. If I know my unit circle pretty well, I can even do the cotangent of the 2x row in my head. But even if I don't know my unit circle at all, I can type cotangent of pi over 4, and it's going to tell me 1. And then I just go one extra step after that. And I depend less and less and less on my calculator. I am a big proponent of not needing a calculator as much as possible. Obviously, we're going to have it. There's nothing wrong with technology. It's just technology can be faulty. Had a student in my last class take a test, and they didn't know how to simplify fractions on paper, and the calculator that they brought didn't do the conversion from decimals to fractions, so when they typed it into their calculator and they got a decimal out, they didn't know what to do with that. And it's because they hadn't mastered the material well enough to be able to do it on paper. So big proponent of minimal calculator use. That's why you'll never find on your assignments that I do any of the, like if you look through your book and stuff, there's all these problems where it's like, use technology, graph these things, do this and this and this with technology, which is wonderful. But our book, and the way that we approach trigonometry is we don't use a lot of the technology for that. We use that later on in calculus and stuff like that, because it's better to have a strong foundation without a calculator. So once you get down to that bottom row, or you do the computing however you choose to do that, I find that at 1/8 I'm at a positive half, I'm at 0 at pi over 4, and I'm at negative 1/2 at 3/8. Are there any questions on that one? You can kind of see it, because this one did have a vertical shrink. You can kind of see that this one is a little bit like wider and fatter than this one up here, because that's what happens if you get shrunk vertically. You go wider and fatter. Any questions before we move on to the big one? Our first one only had a horizontal stretch and shrink. This one had a vertical stretch and a horizontal stretch. Our last one is going to have a couple things going on. Yeah, we'll leave that out. We are going to graph y equals -2 minus cotangent of x minus pi over 4. So all kinds of stuff is going on in this one. And that's okay. From college algebra, or from 2.5, the translations of functions, also from the stuff we learned in 4.2, where we did the translation of our sine and our cosine functions, what we know is that this -2 that's out here in the front, this is a vertical translation, and it's going to shift my entire graph down 2 units. Inside, I have an x minus pi over 4. Notice I say inside because it's inside the set of parentheses, so it's inside of the function. This is a horizontal translation. And remember, the horizontal translations, they go the opposite direction that you would think. So if it's minus pi over 4, that means we're shifting everything to the right by pi over 4 units. And the last thing we have to be aware of is this negative that's out here. That negative, albeit it is a 1, negative 1, it's still talking about something that's going to happen vertically. And this is a translation or a reflection that's going to happen. Do you have to know what all of these different things are? Not necessarily in order to graph. I will say on your test there is some where I ask you what kind of translations are occurring, and I give you an equation like that, and I say identify all the translations that happen. So I'm not going to ask you to give me all those translations and then graph it, but I am going to ask you to recognize what types of translations are occurring. So if looking at that, if you can't identify what's going on, open up 2.5. Open up the college algebra textbook and go to 2.5. There's nice, wonderful tables. Or go back to 4.2 and look at the different translations that we did with our sine and our cosine function, because these are the exact same. Since this is our cotangent function, I guess it doesn't really matter if it's tangent or cotangent. We have our period, which is pi over b. Our b in this case, there's no number here in front of our x, so we assume it's 1, so we have a regular period of pi. Now, when we go in to actually solve these, I told you that the only thing that's going to affect our asymptotes is if we have a horizontal shift. So the way that you're going to want to approach this is if you think about our generic graph, or our generic form here, we have a cotangent bx. Like, that's our generic form, right? So when it says bx equals 0, it's anything that's inside of our cotangent. That's what you're going to set equal to 0 in order to solve for your asymptotes, okay? It's not just that b in this case is 1, and so it's 1x equals 0. Don't do that. It's anything that's inside of our tangent or our cotangents. And so you definitely want to make sure that you're including that. So here I didn't just put, well, x equals 0. It's x minus pi over 4, because that's everything that's inside of my function. And then I did x minus pi over 4 equals pi. And you have to solve those in order to find out where your asymptotes are. So if I add the pi over 4 over, I have x equals pi over 4. And again, if I add it over, I get 5 pi over 4. That's where my two asymptotes are going to lie. And then for this one, I did not use a table, because I wanted to make sure I did at least one problem where I did not include a table, so you can see the other method that you can use to figure out this information that you need to graph these. So instead of using a table, what I did was I plugged in each of my subsections, the pi over 2, the 3 pi over 4, and the pi, into the original function. And then I computed out what my y value would be at that given x value. So I found my ordered pair. I plugged and chugged like we did back in college algebra, where it asked me to test a solution. And then all I need to do is graph those 3 ordered pairs to get my graph of my cotangent. And then I went ahead and I graphed it over 2 periods so that you could see that. In your homework and quizzes, sometimes you're going to graph over 1 period, sometimes you're going to graph over 2 periods. In the test, I believe I have you graph over 2 periods every time. When you do the matching, though, the matching is only over 1 period. Now, hopefully some of you are looking at this and thinking, well, wait a second, this looks like tangent, because tangent rises from the left to the right. Cotangent should fall from the left to the right. And why it doesn't do that is the negative that you can't see. The negative in front of the cotangent makes it a reflection across your x-axis. And when you reflect across your x-axis, then what is above goes below, and what is below goes above. Thus, we get a graph that looks more like our tangent graph than our cotangent graph.